Today we'll go for class 10th. Okay, so yesterday's class we learned regarding the fluorescent lamp. So today we'll go for the next concept of this luminescence property. So luminescence spectra of the activated zinc sulfide. So we have seen the different colors of light we are getting in the market and how it is possible. So zinc sulfide, yesterday fluorescent lamp you have seen, so where the host cell is being outer side of the tube, where it is absorbing the UV light, so that is phosphor. So this zinc sulfide is used as one of the phosphor after irradiation the UV light here. So each activator gives the color, so it depends on the activator what we use in the phosphor. Okay, so we have seen red light, blue light, or yellow light, different colors lights are high because of the addition of the activator in this to into this phosphor. For example, you can see here graphical emission as well as the wavelength here, 4000, 5000, 6000 wavelength Armstrong. Okay, so you can see that the particular light also. So if it get excited at 4000, emits at 4000 Armstrong, so blue, green, yellow, red. So if we dope the phosphor with manganese, so we are getting around yellowish or reddish color. Cobalt will give green, yellow, or silver, blue. So like this. So if we add different types of activators, different metal ions into this phosphor host cell. So when we hit this with UV radiation, so what will happen, there is excitation, and when it excites and when it comes to ground level it emits light, and that's why we see different color bulbs, okay, fluorescent lamps. So this is how it works. And sometimes it will give you white also, so white also combination of two different, so it will give you visible range, white light or so, like that. So how it gets, so for example silver plus ions as activator. So silver is D10 system in the ground state, okay, in the ground state. But when the excited state, what will happen, it will be 4d9 5p. So this is what excited. So similarly antimony plus 3, so D10 system 5s2. So in the excited state will be 4d10 5s 5p. So like this it get excited, and well emitted, so it will give a color, different color. So this is how the mechanism of different colors shown by the fluorescent lamp in the presence of different activators, metal ions. Okay, so this is how. And next concept is of the potential and potential energy versus how this transition takes place with the distance or interatomic distance. Okay, so usually this is a ground state representation of potential energy versus diagram for the liquid crystal ionic of the luminescent center. Okay, this is called luminescent center. Luminescent center if in ionic host crystal, like this simple way. But if you see the ground state as well as excited state, so this is the excitation state. So here A is a ground state and B it is here. So first excited state, then it comes to C, okay, and finally it comes to D here. So that is emitted to here D or E, like this. And here in the excitation one point is here E, so this point it gets attached here. So we will learn about this. So what will happen when the electrons are excited from the ground state, so it will go to the excited state B, then some energy is being relaxed here at the C, and then it comes to ground state D or E with emission the light. So emitted of the light will be there here. Okay, so this is how the works, the luminescent center works, and each of the luminescent has one of its P diagram, potential energy diagrams. Okay, so when it comes, so like this it goes, and the emission will takes place. But sometimes there is a term we use as a thermal quenching. What is this thermal quenching? Thermal quenching is nothing but this point, where that's called spillover point. What happens if we increase the temperature, what will happen, the electron get excited here and directly it comes to E, and then it spillover means like ladder. So from the ladder is now, if we sit here directly we come like this, we play no ladder, and so directly we come here in a smooth place. Okay, so this way, so electron comes here if we increase the more temperature, and directly spills over with releasing all the energy to the host, like this. And there is no emission now, so there is no emission, directly it is coming to here, so without giving any emission. So that point we call it, that's why we call it as a thermal quenching. Okay, spillover point, where we can see the non-radiative transfer of energy, transition, non-radiative transition, there is no radiation, so non-radiative transition. So as we increase the temperature, we don't see any radiations, emission will be not there. Why? Because of the this region, spillover point, and directly it comes to ground state by giving all the energy to the host cell, different vibrational modes. Okay, so this is what's how we can show. So you can see here, so this is how sensitizers when it excitation, so this is non excitation, and activator. So these are the activator, and the energy is transferred here. So this is called non-radiative transfer of energy. Then it comes down here. Okay, so there is no radiation transfer of the radiation. So this is how we can show non-radiative type of transitions here, but there is no emission also. So there is no emission here, it is emitted. This is non-radiative in presence of sensitizer and activator in the luminescent, this one. Okay, so there is non-radiative transfer of energy, then it comes to ground state with emitting of the radiation. But if we increase the temperature, then there will be spill point over and there is no emission, so directly the electron comes to the ground level without with giving all the energy to the host cell, different vibrational modes. Okay, and one thing we have to keep in the mind of what is the phosphor metal, they will ask. The phosphor material is nothing but fluorescent lamp. In the fluorescent, what we use is fluoropatite. Fluoropatite means CaFi PO4 thrice F. So this is a formula here, and it is doubly doped with Sb plus 3. Okay, antimony which gives you blue color, Sb plus 3, and there is manganese which gives orange color. So this is how the floral material, phosphor material is used. Inorganic phosphor material is used. Okay, and doubly doped with something other cations. If we take and doubly doped it, we will get different colors, or sometimes we get white color also. So this is how the phosphor material works. So one more thing in the 2 marks or 3 marks comes, that is called anti-phosphor phosphorus. What does this anti-phosphorus? Anti-phosphor is nothing but opposite. Anti means opposite of the emission. That means IR to high energy level. So low energy to high energy. So in this case we get what emission emitted will be low energy, but here in anti-Stokes we get high energy emission. High energy emission, emitted light will be of high energy. So excitation will be of two more stage here. So best example for anti-Stokes is yttrium fluoride, then sodium lanthanum tungstate WO4. Okay, so W doped with Yb plus 3 as a sensitizer and erbium as a activator. So you can see here. So this is the first excitation state, then the second excitation, then emission takes place. This emission will be of high energy. This will be of high energy, that means low wavelength. Low wavelength. This is called anti-Stokes. This normally what will happen in normal. So we get excitation and small release of time, and then suddenly it will come. So this is of lower energy. Emission is of lower energy. Okay, lower energy means high wavelength. This is a normal. Emission will be of high wavelength. Lower energy is a normal. But in anti-Stokes, emission will be of high energy and low wavelength. So this is called anti-Stokes. Okay, this is that's why it is called anti-Stokes. So this is what the difference between the anti-Stokes and Stokes. Okay, Stokes ships, like last class we have learnt. So this is what about the today's class regarding the luminescent behavior. In the next class we will see some other concepts of this optical properties. Thank you.